Welcome to Stories from the NNI. I'm Lisa Friedersdorf, Director of the National Nanotechnology Coordination Office. In this snippet, taken from our earlier conversation, Kurt Kolasinski, Professor of Physical Chemistry at West Chester University, discusses his approach to incorporating nanotechnology into the classroom.
I like to infuse the physical chemistry curriculum with examples of nanotechnology and nanoscience, rather than teaching it as some separate little add-on thing where, oh, all of that was the important stuff and the regular stuff, and here's this little kernel. No, there are places where it shows up all over, because so much of nanotechnology is very often tied up in the interactions of light with matter. And those are wonderful ways to bring across how restructuring a material can change its optical properties, because we're so in tune with how we see the world. You know, when you understand something, you say, I see. And so when you bring up an example of structural color in butterfly wings, people really do see that. Sometimes we have these preview days when high school students come by and do they want to study chemistry here, and they take a look, and I'll show them a wafer of silicon, polished wafer of silicon, and say, hey, this is what we can turn into integrated circuits, like the ones in your phone that are in your pocket right now. And so that's one side of how, well, with fabrication, and of course that's something that's hard to get across, but you can see the wafer here, and oh yes, oh, but by the way, this same wafer that's nice and shiny and silvery, if I put it in front of the laser that we're standing next to right now, and I scan it, I can turn it, oh, here, look at this wafer, it's black. And it's black because I've changed the structure of the surface so that reflected light is reflected forward and not back at you, and therefore all of the light is eventually absorbed. They can see that. They know that restructuring a material without changing its composition has changed how I interact with it. It doesn't have any light coming back at me anymore, and it has turned black. Now let me take that same wafer and dip it in a solution of hydrofluoric acid and a strong oxidant. And all I have to do is dip it in there. And through a self-limiting electrochemical process, I introduce nanoscale pores and with nanoscale less than 5 nanometer thick walls. Then I take a black lamp, like the one that you might have at a dance club, I shine it over that wafer, and it glows yellow-orange or red-orange, depending on the size of the nanostructures. It's something that you can see, and I've changed the optical properties of that silicon wafer, a wafer that we could use lithography and very refined processes to turn into an integrated surface, or that we can dip into a solution and in just a couple of minutes turn it into a quantum-confined structure that emits light under ultraviolet radiation.